My name is Sam, and I'm going to be your host today. Welcome to Astronomy Days, and we get to talk about the Curiosity Mars rover today, so that's very exciting. We have people joining from YouTube and Zoom, so I have a quick tutorial on how to use Zoom. But while I go through this, I have a question for you. What is your favorite Mars rover? Which one is your favorite Mars rover? All right. So again, with Zoom, really quickly, you'll have the options to mute and unmute and start and stop your video. Because this program is recorded, those options are not available right now. But there is also the option of closed captions. So if you click that, you can click show subtitle and then change your settings with if you want to make the subtitles bigger or smaller, whatever you would need. Also, to best view our speaker and their presentation, if you go up to the top right corner, you can click speaker view, and then under view options in the center, you can click side-by-side mode. And that means that the presentation will appear right next to the video of our speaker. And you can adjust the sizes of the presentation or the video by sliding that little bar on the side there. And finally, there is our chat. I'm seeing a lot of people using our chat to tell us their favorite Mars rovers. Thank you. We've got Spirit and Opportunity, and yeah, wonderful. And so please use that chat to comment, make observations, and ask questions that are relevant to what is being talked about right now. But again, please remember to be a good digital citizen and be respectful of the presenter as well as your fellow attendees. And with that, I am very excited to introduce our speaker for today. Ken Brandt is one of our fabulous solar system ambassadors. And thank you so much for speaking with us today. I'm going to stop sharing my screen and let you take it from there.
I'm muted. Okay, let me get my screen, get my stuff together here, and
yeah, no worries. And we're seeing some great answers in chat. Perseverance was also mentioned as their favorite Mars rover.
All right.
Fabulous.
Can everybody see, and one of the hosts, or Sam maybe, can you tell me if you're seeing my screen?
Yes, we are seeing your screen. Mm-hmm.
So I want everybody to get their serious face on for a minute, because this is serious stuff. The next week in space exploration history is a rough one for NASA. During this time, over 7 days between now and the 1st of February, a total of 17 different astronauts have perished trying to explore space, some closer to Earth than others. And the three I'm going to ask for a moment of silence for in a minute died in the Apollo 1 fire 55 years ago today. And they weren't even in a spacecraft. They were in a mock-up of the command module they were going to fly in. And there was a fire inside the capsule that consumed all three souls aboard. And so I'm going to ask for a moment of silence, please. Thank you. We learn from our failures. We also learn from our successes. And of course, one of the big successes in NASA's pattern of space exploration is to, okay, I'm trying to put this on the bottom. Okay, so where is that setting? Excuse me. Okay. There we go. So hopefully that will move it to the bottom. There. Okay, so this is the title slide. You can see my email down. Hopefully you can see my email down here at the bottom, and you're seeing my cursor, because I'll be using the cursor to point out cool features of the robot Curiosity and other things about Mars. Most importantly here in this slide, this laser that's actually able to shoot where Curiosity can't go, and then can go in some cases, but it's out of the reach of its robot arm, which is pretty long because that's 8 foot out in front of the rover. So the rover can roll up to a cliffside and actually aim the laser up and shoot and get rock samples going all the way down the depth of a cliff, of say sedimentary rock, and I'll show you one of those in a few minutes. But Curiosity is learning a lot about the story of Mars water in this one particular place. Oops, okay, there we go. Now this is the complete fleet of rovers plus one interloper here in the middle. I couldn't Photoshop him out for some reason. Anyway, but you've got all the successful rovers that have landed and deployed on Mars. Now, the Mars 3 down here in the very bottom, the little one, that's actually a Soviet rover. It was actually the first rover to land on Mars. It only worked, however, for about 20 seconds and sent back part of one image. So, not terribly impressive, but they were able to land it in one piece on Mars. And that was a huge insight that, yes, you could land a robot on Mars even with Mars's thin atmosphere. Most of these landers use a combination of retro rockets. Spirit up here at the top right and Opportunity down here in the bottom foreground, both used airbags. Once they used retro rockets to slow it down to a point where it's about 90 feet off the ground, and then they snapped the cord and deployed airbags, and the rover bounced to a stop after coming down. And then it played a game of origami, because it started out as one big four-sided pyramid and turned into a rover with wheels down and solar panels up, so to speak. So this is where Opportunity rests today, because Opportunity stopped working about 2 years ago during the middle of a global dust storm, the likes of which no one had ever seen on Mars before. And of course, since Opportunity is solar powered, the drain and power caused by the clouding of the sun by the dust and the deployment of dust particles on the solar panels was a 1-2 punch that took the rover out, because that dust storm lasted for about 6 months. It was sending signals back for about the first 3 months, and then it stopped sending signals back one morning. And so this is the drive path of Opportunity, and I'm so proud of this thing because it still holds, even over Curiosity and Perseverance and everybody else, it still holds the land driving record off-world. It beats the lunar rover from Apollo 17 by about 3 miles. So this rover, during its time on Mars, over almost 15 years, drove 28 miles and lasted almost 5,200 Mars days, or sols. So what we call a day here on Earth is a sol, because it's the time it takes for the sun to go all the way around one time. But of course, we don't call it that. Just like we don't call the truthful thing that happens at the end of the day, or apparent sunset. We just call it sunset, to shorthand. But that's really a lie, because the sun isn't moving. The sun isn't setting anywhere. The Earth is moving out from under it. Anyway, so this might have been Opportunity's lasting impact, because Opportunity and Spirit, and even Sojourner, when it was deployed in 1997, NASA had a very open policy about the web. They said, we're going to share these images as quickly as we can. So if you go to any of the active rovers, or inactive for that matter, rovers webpage, you can actually see the raw images that they took. And I like to tell my students, if they see me before 11 o'clock in the morning, I tell them, if you go to the raw images site for Perseverance or Curiosity, you are actually seeing the images before the mission team does, because they get to work at 8 o'clock in the morning, California time. So they're not firing up their computers so they sit down at their desk or whatever, or, with their coffee and muffin at breakfast if they're still at home, which they are, actually. They share everything out on the web the night it gets downloaded from Mars. So Mars, typically a rover will send information up to an orbiter. The orbiter will then tag team it to Earth, will download, and then it will come out as 2 trunks when it comes out to JPL. One trunk is for the scientists and engineers who are actually working with the rover, the science team, and the other chunk goes to the web. It gets looked at, make sure there's no gross processing errors, and then posted. So everything the rover sees, you see the next day or sooner. And this is really cool because the rover, Opportunity took us on a tour of Mars, and a big piece of Mars, 28 miles worth, right? As we already talked about. So, Opportunity was basically taking everybody for a ride on Mars. And this is pretty cool. I mean, it's pretty neat how NASA does this. Not to diss the Chinese space program, but when Zhurong sends back images from Mars, those things are carefully looked at before they're finally, weeks later, put onto the web. After they've cleared propaganda and all that other good stuff, they got to clear, the sensors, basically. Did I say that out loud? Sorry. Anyway, Curiosity's major goal is to look for biology on Mars, or the evidences of biology on Mars, is to interrogate the chemistry of the rocks, figure out the story of the water on Mars, and also has an instrument aboard to gauge radiation levels for future human explorers, because radiation is a big concern on Mars, where this thin atmosphere doesn't filter out ultraviolet rays from the sun. Even though they're less powerful because it's further away, more of them get through the atmosphere, more of the other rays too, that can damage or even destroy DNA, for one thing, or cause all kinds of mutations and stuff. Okay, so Curiosity landed almost 10 years ago in August, and as you can see, Mars is a dirty environment. Everything on the deck of this rover here is supposed to be white, okay, except for the occasional metal fittings or whatever. And you can see that's not white, right? That's like, after a day of playing in the mud. Well, Curiosity kind of plays in the mud because the rock underneath Curiosity in this image is actually mudstone, kind of shale that forms in river mud or lake mud. So Curiosity is driving over these panels of sedimentary rocks. And you can see over here a sense of the outcrops. So we'll talk more about the rocks and the laydown of Mount Sharpe here in a minute. So we're almost 10 years on Mars, gone over 17 miles. This is an image taken last year. They haven't updated this particular idea yet. But this is Curiosity after about 3 months on Mars, looking off into the distance to its path going up the hill. It's climbing the side of this mountain called Mount Sharpe, which is about twice as tall as Mount Mitchell in the western part of North Carolina. So it's almost 13,000 feet tall. So big mountain. And they're going to climb as far as they can. They're basically going to drive it till it breaks. That's the robot drivers have that philosophy. We're gonna make it work. We're going to find out what the limits of this thing are on another planet. Because when you do that, what do? You expand the field of exploration. Sam, are there any questions coming in or no?
Yeah, we have a couple. We had a question about where is Curiosity now, which you kind of answered with the mountain. But did you say where the mountain was located on Mars?
Yeah, it's located in a crater called Gale Crater. I think I've got a global shot of it, not global, but a regional shot of it later.
Cool.
But it's a crater, and it's most of NASA missions are launched within 10 degrees north or south of the equator. And in the case of the solar-powered stuff, you need that because you're deriving power from the sun. So you want it as high overhead as possible for the maximum, what they call in Earth science, insolation, INSOL-ation. The other thing, too, so everyone is within 10 degrees of the equator because that's where all the comm relays are set up for. With all the different orbiters, they're all set up to orbit at a significant amount of time in that plane so they can receive data from the surface landers. So that's also why they had Apollo within 15 degrees, I think it was, of the lunar equator for the same reason, make the communication easier. So like most of us, and there's a picture of Curiosity again off to the right. Most of us have been working from home off and on since March of 2020, as you know. The people at JPL are still working from home. They have not yet resumed going to work, except in a limited capacity, like for emergencies or whatever. Then they go on campus. And they phone in ahead of time and say, I am coming on campus. What time can I come aboard? So we're not, they'll tell you may arrive at 10:30. Do not get here earlier because there's other people that have to go in there. So, all right. So this is a video tour of Mount Sharpe. And I think we get the global answer here.
NASA's Curiosity rover went to Mars to explore Gale Crater, a large impact basin with a massive layered mountain in the middle. How did this strange landscape come to be? And what can its history teach us about the potential for life on Mars? After several years of exploration, here's what we think could have happened. Around 3.7 billion years ago, a large meteor impact blasts out the initial crater, cracking the rock below and leaving a central peak as the surface rebounds. It's a wetter time in Mars history. Groundwater seeps into the new crater, while rivers fed by rain or melting snow also flow in. forming a large lake and carrying in gravel, sand, and silt. This material keeps building up over millions of years, and as each layer cements into rock, it records a snapshot of the environment that shaped it. In time, the gradual drying of Mars shuts off the rivers, but sediment keeps piling up as sand and dust blow into the crater, deeply burying the deposits laid down in water. Meanwhile, groundwater remains deep below the dusty surface. At some point, winds that once carried sediment in begin scouring it back out. In areas closer to the crater rim, these winds dig all the way down into the ancient lake deposits. And as the heavy weight above is lifted, these layers crack, which helps groundwater flow through and alter them again before they dry out. By about 3 billion years ago, we're left with the basic form we see today. And it's in this version of Gale Crater that Curiosity has helped piece together the story. Sediment patterns show a lot of water was present, continually, over many millions of years, both as persistent groundwater and a long-standing lake with occasional dry spells. Mineral and chemical readings show that water from both the lake and subsurface was friendly for potential microbes. Drill samples from the lake bed show key elements, organic molecules, nutrients, and energy sources that microbes could have used. Water flowing through underground fractures could have supported life even in deeply buried rocks. And the composition of some layers makes them good for preserving potential signs of past life. Taken together, the evidence points to Gale Crater, and Mars in general, as a place where life, if it ever arose, might have survived for some time. With our primary mission fulfilled, we continue exploring, uncovering the history of Mars and learning more about how and where future missions can search for the signatures that ancient life may have left behind.
Okay. All right, Sam, you said there were a couple of questions, and I realized in the middle of that video I'd only answered one of them.
Yeah, no worries. The only other one we kind of mentioned in chat, but Aaron was asking if Curiosity and all the other robots were stuck on Mars right now.
Oh yeah, and they are truly stuck. It's a one-way trip. When you send a robot to Mars, there is zero expectation of getting it back, except, of course is an exception to the rule. Perseverance has sample tubes that it's laying down on the Martian or storing in its carousel inside the rover. And a future sample mission, probably in about 8 years now, will be deployed to Mars by NASA and the European Space Agency to pick those samples up, shoot them into orbit, hit an orbiter on a path back to Earth, and then send them back to Earth by about 2031. So in about less than 10 years, we will have a much deeper insight for what we know about Mars. But the video showed you a couple of what I call tortured terrains. There's a better name for these in geology, but I'm forgetting what that is right now. If you look over here on the bottom center right, you see these layers of rocks that have what are called a dip. That is, they're bent relative to the normal, because you have to assume gravity works all the time. So gravity tends to deposit layers horizontally, one after the other, and you get a really nice indication of who is the oldest, because all you got to do is keep digging down till you get to the bottom layer. That's where you start. That's the oldest, and then you work your way up towards the surface. So these rocks down here next to the sand are way older than the rocks up here next to this other bed, which is inclined at a different angle. So you got two different angles of bedding here, which indicates that the rock, after the rock was formed, Mars underwent some folding of the crust. So there's some folding going on here. Now, is that folding from an impact, from a meteor, or some tectonic process we have not identified yet? Don't know. You know, it's the nice thing about Mars exploration. For those of you tuning in who are young and have yet to pick a career, this is not a bad one, because there's still a lot of questions we have to answer about Mars. We haven't even started this yet, because every time you get more information, what's the first thing that happens? Boom, all these other questions. Oh, okay, silicon's in that rock. How did the silicon get there? You know, or there's these little things that look like bacteria in this meteorite. How did they get there? You know, and then you have to answer more questions. Yeah, so anybody who thinks science is done or finished doesn't know how to play science very well. That's all we're going to say about that. All right. Okay, so these are 9.5 years worth of drill holes. There are now 2 more. So you got to know that drill bit on the rover's got to be getting old, because it's drilling through some hard rocks that vary in hardness from like calcite, which is hardness of 3, all the way up to silicates, which tend to be around 7 on the hardness scale. Bad news, you're probably not going to find diamond on Mars, but you never know, right? But these are all the different drill holes. So Curiosity, the bottom line here is Curiosity is a hollow drill bit that takes samples out of these holes and then deploys them to science instruments aboard the rover. And the rover, it's a couple of driving things, can then analyze the samples using about 6 different science lab experiments that are packed into the body of the rover. And they get you a signature, in this case, for an organic compound called chlorobenzene. Okay, now benzene is your typical 6-carbon ring, and all kinds of interesting and weird biochemistry happens because of those things, and the variations on all the different sticks coming off the carbon bonds, because the carbon bonds typically have 2 bonds or 3 bonds here between the carbon atoms, and then a single or double bond out here for something else like oxygen or another chemical group. And that's how you build simple amino acids, for example. So Curiosity figured out that ancient Mars, in many places along its route, has been suitable for life as we know it. Okay. Now, the history of water on Mars should not come as a surprise. Okay. If you think about chemistry and you think about how elements form, you've got hydrogen, most common element in the universe, everywhere, all the time, right? And guess who is element number 3 on that list? Oxygen. So the 3rd most common element in the universe. Helium does not count because helium doesn't play nice with anybody. Helium is what we call a noble gas, doesn't combine, see ya. So we're just going to talk about number 1 and number 2 in terms of most likely to compete or combine. That would be hydrogen and oxygen. So you should expect to find some form of water on pretty much every body in the solar system, okay? And we're finding that out even in the clouds of Venus. The water is masked with sulfur and additional oxygens to become sulfuric acid. But sulfuric acid is in an aqueous solution there, even in the clouds, if you could crystallize it out or liquefy it up somehow by cooling it down, I guess. All right, so you can take a minute to read this, but the problem with organic chemistry is right away when you see an organic chemical, you jump to the conclusion that it is caused by life. That's because you are geocentric. Okay, you are focused on the Earth first because that's everything you know. So obviously you're prejudiced in how you see things, right? You're prejudiced for Earth. So you're looking for processes like they happen on Earth. Well, guess what? Sometimes they don't. Methane can be formed when you cook olivine, which is a common mineral on Mars, and you bathe it in ultraviolet and you expose it to a little carbon. You can actually produce methane that way. So there are non-biological explanations for a lot of these chemical elements and compounds we're seeing on Mars. And Carl Sagan said it best: extraordinary claims require extraordinary evidence. So if you're going to say there is life on Mars, definitively, you'd better have several different episodes of ironclad proof in several different places on Mars, okay, before you go making that statement. We made that mistake in 1996 with a meteorite, going way postal with it. I even had President Clinton at the time do a special address to the country about finding life on Mars. Maybe, maybe not. It could be, but we haven't found another one that's like it. So you can't say definitively that there was life on Mars yet. It's kind of like a murder mystery where you're building up all these clues to a suspect, but you don't have the body. Without the body, you can't make the arrest, right? I think that's how that works. I'm not sure, but you can't make the conviction. Let's put it that way. You got to have the body. Otherwise, your murder case goes nowhere. So in this case, we don't have the living bodies of the organisms that live or lived on Mars. That would be the definitive proof you need. So when you bring these samples back, the Perseverance is digging up in the lake bottom of Lake Jezero. If they show biosignatures that can be identified as coming only from life or the process of life, then you got it. So we might have that answer within 10 years. Okay, so Curiosity is now split in layers here. We're going up from one layer to another, and this is video all about that. Try that again.
The terrain around the Curiosity rover is beginning to look very different. The rover has driven over 16 miles since landing in Gale Crater in 2012. This view is from 1,500 feet above our landing site. We're climbing the side of Mount Sharpe, a very tall mountain in the center of the crater. All of this dark material is Martian sand that's made up of broken bits of volcanic rock. Can you see the ripples that were shaped by the wind? We had to drive around this massive sand sheet as we climbed Mount Sharpe. Look how clear the air is. That's because it's winter when there's less dust in the atmosphere. You can see all the way to the rim of Gale Crater, which is about 20 miles away. We spent the last several years investigating clay-rich rocks that formed in lakes. But now we're entering a region where rocks are filled with salty minerals called sulfates. These minerals form in drier conditions, so we think this area might show us how the ancient Martian climate was changing. We're starting to see lots of very cool, knobbly textured rocks like these. We think these veins and nodules were created by groundwater. Here, we recently drilled our 32nd sample of the mission. By studying the chemicals and minerals in this rock, we can learn how the ancient environment was changing as we go from the clay region into the sulfate region. And these hills are different from anything we've seen on the lower mountain. They're rounded, unlike the ridges and mesas we've seen before. Now let's look ahead to where we're going. We'll soon be entering a narrow valley that should make for some amazing images. On the left is Rafael Navarro Mountain, named after one of the mission's scientists who passed away in January of 2021. This nearby hill is huge. It's about the size of a 4-story building. This changing terrain is more than just fun to look at. It can teach us how Mars lost its water over time. How long did conditions that were favorable to life last? We're looking forward to finding out.
Okay. So this is a schematic showing the possible formation of the layers that you're seeing in these images of Mars. So this is a modified geological map of the surface of Mars here, and this is the part Curiosity is driven through, and it's coming through here. So it's on the way up the side of the mountain on Mars. And then, of course, you have this outflow channel here for what looks like a river or a dry riverbed or arroyo, as you call it out west. Is another potential place where we might find some biosignature kind of chemicals here. This is the red link here. You might just want to take a screenshot of this picture, and I'll reduce my because my gallery is in the way here. If you want to take a screenshot of this picture in the links, you can see the gray rock here. You know, we think of Mars as kind of a rusty red color throughout, and it's really not. When you look at Mars' surface where the sand has been scoured off here, this rock is definitely grayish in hue. And we've got all these white veins of what look like gypsum interlaced. And that's probably where groundwater percolated up through the rock and then deposited the crystal or the minerals that were in the groundwater and then dried up. And so the minerals remain, and they show us the traces of the cracks where the rock was where the water flowed a long time ago. So we all know that evolution takes time. You can't do this between now and 6,000 years ago. All right, you have to have time for organisms to develop, for life to happen, for all the changes that happen that we're used to here on Earth. And on Mars, we don't know how far that got. The guess is, or the inference is, not very, because Mars has been geologically dead for a long time. So if life has arisen on Mars, it's most likely very, very simple. The kind of stuff you have to see through a microscope. Okay. So the last slide I have in my program, I always like ending with this, because this is the Martian sky just after apparent sunset. And this bright dot over here, next to this bright smudge, is actually two dots if you look really close at that image. That's the Earth and the Moon, as seen from Mars. So the Earth is like the evening star and the morning star on Mars. So it's really bright. So at this point, I'm going to stop sharing my screen and ask if there are any questions.
Yeah, we've got a lot of questions, and we also have a lot of observations in chat about how cool it is that you can see Earth from Mars.
Oh, isn't that
like
great?
A star.
It's so cool.
Yeah. So we did have questions, and which you also kind of just answered with, if there is mud that has been found on Mars, there's a chance that there's still water deep in Mars, and I think we have found like frozen surface water, correct?
Yeah, there's a lot of, well, of course, the ice caps, right? Start with those.
Yeah.
And then the European Mars Express has seen all kinds of evidence for subsurface glaciers. So the sand has been deposited on top of this ice on the surface. So, and that goes all the way down to the mid-latitudes of places on Mars. So down near where we might be exploring. Phoenix actually landed, when we landed the Phoenix lander in 2007, it actually landed on a pad of ice near the North Pole. So that was pretty cool. Yeah. So it actually landed on an ice, a block of ice.
Yeah.
Yeah.
Another question.
There's also a lot of underground lakes that they're discovering using ground penetrating radar under Mars.
Oh, very cool.
Okay.
Yeah. So, and as more technology comes out, if we're able to send more things, we'll find more, which is really exciting.
Yeah.
Yeah. And we do also have a question on the opposite side of the spectrum, where if there's, water, are there active volcanoes on Mars? Do we know?
Not that we know about yet.
Okay.
But there's been no overt evidence of a volcanic eruption, what we have going on in the South Pacific right now here on Earth. So no, there's nothing active that's been detectable so far. But one of the missions that went to Mars is called InSight, and Mars InSight is designed to detect Mars quakes, like earthquakes, but on Mars. So we have to call them Mars quakes. And so it's got a seismometer aboard to measure, and they found some intriguing seismographical signatures. None of them are suggesting volcanoes yet, but that's not completely out of the question.
Okay. Yeah, so it's something that we still have to discover. Very nice.
Exactly.
Okay, we have a question about the build of the Curiosity rover. What is the drill made of? Because you mentioned it had to drill through like hardness of 3 to hardness of 7. So
it's a titanium alloy, but I don't know enough about the metallurgy to go any further than that. I just know it's got titanium and steel. Yeah.
So it's a very, very strong metal. All right, very nice. Yeah. So again, almost 10 years of drilling through.
Yeah.
Got to wear that titanium down.
That's a lot.
All right. We do have a question about a question from, and I might be mispronouncing this name, I apologize, but Keenan is asking, will there ever be rovers as large as Curiosity on other planets or moons? For example, they said on Saturn's moon, Titan.
Actually, Titan is a subject of an upcoming NASA mission that got selected this year called Dragonfly, and you'll hear a lot more about that in another Astronomy Days program. I think Doug is doing, one of the other solar system ambassadors, Doug Lively, is doing a program about Dragonfly. That is definitely worth watching, because they're basically taking a minivan-sized drone and landing that thing and then landing it again all over Titan. And of course, Ingenuity is laying the groundwork for this, But flying on Titan is a whole boatload easier than it is on Mars, because Mars's atmosphere is very thin, not a whole lot to catch to provide lift in the atmosphere. But on Titan's atmosphere is way thicker than our atmosphere here on Earth, so it is easier to fly. They theorize that, properly suited up, so you're protected from dying or freezing, you could actually get wings and fly on Titan. Jump off a cliff and just fly around for a while, because the atmosphere is so thick, it would hold you. Yeah.
That is
while
very
you're
cool.
flying. So,
so that's something that you also...
definitely, it would be very easy to land a rover on Titan, comparatively speaking. You just have to make sure to land it where it's not wet. In this case, with methane instead of water. But you don't want to splash down if you're trying to rove. If you're trying to submarine, yeah, sure. Splash down's cool.
Yeah. So that's another thing, like when you're exploring, other planets and other moons, you got to consider, like, where are you going to land? what is the environmental conditions?
That's one of the most important things I do with my astronomy students. We go through a landing site selection activity, and they find out how NASA actually picks Gale Crater or Jezero Crater for the places where they want to put these things. And what are the factors they have to consider? Because it's not just let's look for life. It's let's look for life where it's also safe to land. So it's a duel, and the duel is portrayed between scientists and engineers, but they really do get along, I promise. So,
and then we also have a question do we know how much more time that Curiosity will be able to collect data from Mars?
Well, it will be able to collect data for a while. The question is, how long will it be able to move? Barring the unforeseen, anything can fail at any time. When you got 1,000 systems that all have to work right every time, and you automatically go to the redundant component if you have one, and when it fails. Like in the case of Curiosity's computer, and I know Opportunity, they had to reboot Opportunity's flash drive a bunch of times. Now think about it. I can't reformat my flash drive, here. And I'm sitting in front of my computer, and I have the entire World Wide Web to help me. On Mars, they actually reloaded the Opportunity memory software from Earth by radio waves. That, to me, may be the most mind-blowing thing about this whole exploration thing. They're actually able to reboot and restart a computer on Mars. That's pretty cool.
Yeah, that's incredible. Yeah. What technology has been able to do now?
Yeah.
Okay, so we have a question, and we may need to clarify this a little bit. Aaron was wondering, will Curiosity overload with samples of rock? And so I don't think Curiosity is taking samples of rock, correct?
No, and I was sorry, I got drifted away there, and I forgot to answer the whole question. We're just going to blame the post-surgery meds and leave it at that. Anyway, it should last for at least 25 more years. The plutonium that provides the power should last for at least 25 more years. But after that, it will come down to they'll have to start rationing power and deciding, like, drive one day, shoot images the next, send them back to Earth the third day, drive, image, shoot, So they might have to take turns with the data instead of what they're able to do now, which is basically I can take data and send it up at the same time because I got power to spare,
Yeah, so we still got a few years, provided that all the environmental conditions and
and
everything.
the wheels don't bust.
Yes, still got a while yet.
The wheels don't fall off. Yeah.
Yeah. So for the Curiosity, with the samples that it's taking, it's mostly taking like computer data and pictures and things, correct? It's not taking like actual physical rock samples?
It does. It takes the powdered rock and drops the rock into the chemistry labs. In one case, the same instrument, I believe, you vaporize the sample, you turn it into a vapor, and then the different gases go through the chromatograph at different rates. And that's how you develop a spectrum for the materials that are in, not a spectrum, but a chromatograph of the different minerals that are in the rock. Okay. So there's all kinds of stuff going on in those samples. The only thing that's not happening, they're not coming back to Earth.
Yes. And is there a chance that it will ever like overload on the amount of samples that it has?
I don't think that's possible.
Okay.
Because they're very specific about when they drill and what they're drilling when they go. It's not just park and drill somewhere. They park and they look at the rock and say, we're going to drill into this one, take a sample, and we're going to use one of the 20 sample canisters that we have for this particular instrument, whatever that might be. But once you run out of sample tubes, you're done. with that particular instrument.
Okay. All right. Wonderful. And then we also have a question. If there's another rocket or another program that's being sent to Mars to pick up Curiosity, how will they find Curiosity?
Well, that's very unlikely. Okay. What's way more likely is that people will settle on Mars, and after they've been there a while, somebody will drive their all-terrain vehicle out there and put a science museum over it. Make a dome, make the dome inflate it with air that we can breathe, and then have people visit Curiosity. Much the same way you might go to the Jefferson Memorial in D.C.
Yeah. Okay. Cool. And I think. We have another one. If microorganisms are found on Mars, would those microorganisms be considered aliens?
That depends. Here's your wacko theory for the day. You ready? You and I might be Martians. Okay? We might have a lot more in common with this guy than we think we do. Because life may have started on Mars before it got started here on Earth. Because Mars was warm and wet for life at a time when we were still a hot volcanic mess here on Earth. So, Mars may have developed life first, and then you have something plowing into Mars, blowing pieces of Mars out into space, and some of those pieces happen to fall down to Earth. Okay? So you can think of them as seeds, right? Wow. You got this fertile environment here on Earth, and the spores germinate or whatever, and now you have Martian life on Earth. It's a theory called panspermia, and it just simply means that life gets spread out by different impactors going across the solar system, or the Milky Way, or the universe for that matter. But so that's one possible means we might have actually got our start on Mars.
Wow.
Okay? Yeah,
that's so cool. I've never heard that theory before.
No, it's still being worked out. Yeah. It's not like the law of panspermia. It's a theory. Yeah. I'm still working the details out on this one, but it makes sense when you think about organic compounds and how common they are. It makes sense that they would form in many places all over the universe. Mm-hmm. Carbon's number 4 in terms of most common. Nitrogen number 6. So when you start talking about carbon, nitrogen, oxygen, and hydrogen, you got 18 or 20 amino acids right there. Now that's protein. So you got a workable protein system. Now you just have to work on a way to make more of it. And that whole replication thing is the other key. Yeah. And that's a little harder, as we all know.
Yeah. Okay, I think we only have one more question. If y'all have any more questions, feel free to type it in chat now.
I've got a couple more minutes, but I've got to bug out pretty soon.
Yeah. Aaron was wondering, what would happen if you put a pie on Mars?
What kind of pie?
Oh, that's a good question.
I mean, it depends. If you're doing lemon meringue, it's going to behave really differently than, say, pecan. Or that's pecan, true. Excuse me. Yeah. We're in the South, so pecan.
Yes, that's true. Aaron specifies an apple pie.
An apple pie. All right. Well, Aaron, if it's got a crust, first off, the apple pie is going to rest gently on Mars because gravity works. It also works on Mars. So it'll be sitting there, hopefully on a flat surface where it doesn't spill out all over everywhere. Okay. The short version is it's going to freeze and then desiccate, and I'm not sure in which order because Mars is cold. Mars is also exceedingly dry. So all that water you poured into the production of your apple pie and, whatever else you put in there, the apple juice itself, is going to be desiccated in the atmosphere. And what you're going to end up with is beef jerky apple pie. Apple pie jerky. So I don't know what you think about that. That's cool, not cool, whatever. But that's what happens to it. And too quickly. It wouldn't take very long because, the diffusion works, especially when you have no atmospheric pressure. The positive pressure coming off the pie is going to be pretty significant. It won't dry out in a hurry, I think.
Very nice.
It could just freeze. And so you got a freeze-dried pie waiting for you when you get to Mars.
Yeah, Aaron says cool, and it will literally be cool. Yeah.
Minus 100 degrees cool. Yeah. Depending on where you are. Yeah.
Yeah. A freeze-dried pie. Yep.
I'm sorry, Marcel. That's the best I could do.
That poor pie. No. That's a great theory.
Yeah.
All right. Wonderful.
It's an easy way to visualize it. Yeah.
Yeah. Fun.
How high can you jump on Mars? Okay, well, Sean, it depends on what your vert is here on Earth, okay? If you got a vert of about, say, what is the average for a good basketball player? Anybody know? Because I don't know. Okay, I've got a vert of about 2 inches here on Earth, okay? I could pull down a vert of about 6 inches on Mars because Mars's gravity is only 40% of ours. So take your mass, multiply it by 0.4, and that's how much you would weigh on Mars. So there's Ken Brandt's miracle diet and exercise plan, available free from nasa.gov.
Jump higher on Mars.
Yeah, jump higher, doesn't change your BMI at all because your mass is mass, but it does change how much the scale says when you step on it with the spring-loaded things.
Yeah, you'd also feel kind of lighter, right? Because you're not pulled down.
Probably, yeah. Well, then again, you're weighed down by your boots, your suit, your oxygen,
that's true.
water tank, your helmet, all the other gizmos. You have the camera, You start putting stuff on an Apollo class spacesuit, and we're talking maybe 100 pounds. So any weight you might have lost is gained by what you got to wear to live out there. I mean, freeze-dried eggs. Okay, let's get that down there.
Yeah, we're talking about all the food headed to Mars.
All the food. Okay, all right.
all right. So wonderful. I'm going to share my screen for our final little wrap-up slide here. But thank you so much for speaking with us today, Ken. That was fabulous. Learned a bunch.
Hopefully I get to win one of those Friday night at trivia.
Oh, yeah, I know that is one of the options. Yeah. So I wanted to thank our sponsors for Astronomy Days, the North Carolina Space Grant, as well as Pepsi. And as always, thank you so much to our members of the museum who help make events like Astronomy Days happen. We do have this t-shirt on sale. It's a wonderful Venus design this year for our Venus theme. Members can save 10% if they would like to buy that t-shirt, as well as, like Ken said, with trivia, you may have a chance. Possibly.
I got to time out real here. I got to answer this question from Sean.
Oh, there's another question? Go
There's
ahead.
a question. Sean asked, will duct tape stick on Mars? Sean, duct tape sticks everywhere, okay? When they went onto the moon and they busted a fender, they used duct tape and an old map to fix it on the surface of the moon. So, if it works there, it's going to work on Mars. So no worries. Buy up all the duct tape and bring it to Mars with you.
Yeah, duct tape holds the world together, and other worlds together. Yeah. Wonderful. And yeah, so thank you everyone who attended this program as well. We have another great program scheduled for today at 6:00. It's a history of Mars exploration. So it's super appropriate considering we just talked about a bunch of Mars exploration. Get to learn some more about that. We'll post a link to our schedule with how to register for the programs in our chats. And the recording of this program will be posted on the Astronomy Days program page as well as our YouTube. And thank you all so much for attending, and we hope you have a great rest of your day.
All right. Semper Exploris.
Yeah, always.
Always.